And again, the last part we are asked to draw our power flow block diagram. And the reality of it is that, very often it's a good idea to start with that and put all your given information on it. And that very often helps you with the solution to the rest of the question, right? Because once you got that visual in front of you, the calculations probably becomes, well, more or less straightforward when you got that in front of you, right? And so I'm going to go ahead and do the calculations before I pulls in the block diagram of the power flow through the motor. But again, right, you got your values here, all your losses are listed, and we'll use this value here for power out. And so, the power flow through the motor gets you through the calculations. Okay, so part A, real reactive and apparent power delivered by the AC source. And so we got to work that out, right? And so we'll start with, we're told it operates at full load. So if that's the case, power out then is approximately equal to 200 horsepower. And of course we need to convert that value to watts. So 200 horsepower times 746 watts per horsepower, and P out then is equal to, and the power out value is 149.2 kilowatts. Now, I can, I guess, calculate the total loss. And remember that the rotor loss is not specified because that's supplied by the DC source. And therefore, it's the AC loss that we're going to calculate. And the losses in the stator and in the shaft, we assume come from the AC source. And so that gives us then an iron loss, a stator I squared R loss, and I'm forgetting my stray loss because that one's a bit new, specific to our synchronous motor, and then the windage and friction loss. So our AC losses then, the iron loss 2 kilowatts, the stator I squared R losses 3.5 kilowatts, and so we'll include all of them really, right? The rotor loss is DC, of course that one don't go here, but we don't have that in our list, right? The stray loss is 1 kilowatt, and the windage and friction loss 1 kilowatt. So the total is 7.5 kilowatts. Now that gives us then an AC power in equal to the mechanical power out, which is supplied by the AC source, plus the AC losses, and so our 149.2 kilowatts plus the 7.5 kilowatts of losses, and the power that comes from the AC source, the real power, is 156.8 7 kilowatts. Okay, so now we need also the apparent power, which remember is S, and reactive power, which is Q. And again, this is a synchronous motor. We're not told, oh yeah, we are told it's lagging, which is normally then, see 0.9 lagging is a good acceptable spot to have that adjusted to. Doesn't give you minimal stator current, but it gives you a good acceptable power factor at 0.9. Now, so next we looks up here and we don't have a current, but we do have a power factor. So that means then that S3 phase, remember it's our pattern use, so the AC power in divided by the power factor. And again, right, the DC power don't come into account because we're considering the AC source only here, right? Okay, so now we have 156.7 kilowatts, and our power factor was 0.9. And the fact that it's lagging, leading, don't affect the calculation. S3 phase then is equal to 174.1, and our unit for that is kVA. And so now Q, Pythagoras' theorem, third side of the triangle, and it's QL here because we told it's lagging. So the square root then of S3 phase squared minus the AC power in squared. And so now when I does this calculation, I usually just puts in 174.1 squared, subtract 156.7 squared, and when I does that, remember that there is a K, which we didn't include, but we need to include it in our unit for Q, of course. So QL, once we works that out, 174.1 squared, subtract 156.7 squared, we got 75.9, and that kVAR. So now, you know, here, remember that if I'm grading this, I'm expecting you guys to use the proper units for the power. Alternately, I suppose you could label it as real, apparent, and reactive. Power drawn from the AC source. All right. Okay, now part B, we want to calculate the efficiency of the motor. And so remember that the efficiency wants the total power in. So then the DC power in is the rotor circuit, and that is equal to, now the numbers we've been given for the exciter here, right, we'd consider them to be VDC or VX, and IX is the exciting current. And so, you know, we call that V rotor or whatever, VX times IX, and we had 240 volts DC multiplied by 50 amps DC, and so the DC power in is equal to 12 kilowatts or 12.0 kilowatts. So now we want the total power in, and that's simply the sum of the AC power in, of course, plus the DC power to the rotor. And the total power delivered to the motor then, 156.7 kilowatts plus the 12 or 12.0 kilowatts. And the total power in becomes 168.7 kilowatts. Now, the efficiency then is the mechanical power out divided by the total power in. And of course times 100%. So we have the power out, remember up here was 149.2, so 149.2 kilowatts divided by 168.7 kilowatts. And so, you know, if you forget your DC power in, usually the efficiency is off by a couple % or something like that. And so we got this one done. We came up with 88.4% if we rounded to 3 significant digits. Okay, part C asks us for line current. And the line current, then we can take it from either one of the power equations. And so I usually just use this S3 phase divided by √3 and V line. And so, you know, remember here that if you're putting P in up there, is AC P in over √3 times V line times the power factor, and not the total P in, because it's line current, and that means from the AC source, right? The DC current is not part of this one. The DC current's to the rotor, your line current into the stator. And so we have 174.1 kVA divided by √3 and divided by V line, and the rated value for V line is 440 volts, and we use that value because we haven't been given a measured value. And so the line current then comes out to be 228.5 amps I got here. Now, and so the last thing we're asked to calculate is the torque developed. And so very specifically, it says torque developed. And so that is because we don't want you to use power out value. We want you to use PMI or PR, all the same, right? So now if you had your power flow diagram sketched already, you'd have PMI on the diagram, but it's not P out here, it's PMI. And so the speed, of course, is NS because this is a synchronous motor, but still it's PMI. And so PMI, thinking about your power flow, PMI is equal to P out, which of course we know, plus the shaft loss, which is the windage and friction loss. And so we had Remember, P out was 149.2 kilowatts. And in our list of losses, windage and friction was just 1 kilowatt. So PMI should be used for torque developed if we know it, right? And so we got 150.2 kilowatts there. And so that's the number we should be using for torque developed. Like we said, 9.55 multiplied by 150.2 kilowatts and divide that by the speed. Now assume the speed was given, yes, 900 RPMs. And so if you do that calculation, the torque developed is equal to 1,594 Newton meters, or 1.59 kilonewton meters, I guess, if you would. Now, the last part is the power flow diagram. And so instead of sketching that, I'm going to pull it in from the other slide here. And so this is it. Now, so I'm going to pull that over with the rest of our stuff here. And let's see if I says, oh, I should be able to say paste there, right? And here it is. Now, so remember that with respect to our power flow diagram, PM is power out, and that was given. Our windage and friction loss goes on here, and the mat here got to add up and match the mat in your question, of course. So if we add the 1 kilowatt, oh, I got my cursor lost. Okay, if we add the 1 kilowatt of windage and friction loss, right? Of course, we're coming up with PMI 150.2. Now we're going back towards the input, so our numbers are getting bigger. Okay, the DC power in is 12 kilowatts. The rotor loss is also 12 kilowatts, so you should put that value on there, yes, twice. So PR for any synchronous motor, right? We always said that PR is equal to PMI. Why? Because the rotor loss is all supplied by the DC source, so these two values should be equal. So PR then is equal to PMI. Now, in the stator, we have 3 sets of losses. They should all be labeled with a value. Stray loss was 1 kilowatt, iron loss was 2 kilowatts, and I squared R was 3.5. So that gives us 6.5 kilowatts of losses in the stator. We add that to PR, and that gives us our ACP in value. And again, right, all these numbers on this diagram should match up with the numbers in our calculations. Of course, they have to. And remember that you should put the label on there and the value and an arrow to indicate direction for each piece. And our 3 blocks then should be labeled stator, rotor, shaft, right? And so, you know, all these diagrams are very similar. There's a couple of differences between this and the induction motor, because the induction motor, of course, the rotor I squared R loss is PJR, and that's an AC loss in there too, no DCP in. And of course, there's no stray loss in the induction motor.